To look at electric current, first let's kind of think about a wire. So we have a big wire like this. What's happening with electric current is we are, through some potential energy differences, we're forcing electrons to move through a wire, right, and to move around a wire. And that's essentially what electric current is. Our sort of definition for electric current is that electric current is a charge per unit time. We define that with an I. So we could say, right, charge we used as Q. So maybe delta Q over T would be a good way to write it. Our unit for electric charge is amps or amperes. And it's sort of how much charge per unit time is flowing through a certain wire. The other way to think about an amp, our unit here, which kind of makes sense, our unit of charge is a coulomb, time is second, so it's how many coulombs per second moving through a wire, which would make up an amp. Resistance through any sort of electrical object, let's just take just a wire, for example, electrons flowing through this wire, flowing through this way. As these electrons move around through this wire, they're going to sort of bump into the sides, they're going to bump into each other in sort of the way that electrons might. And that's going to impede the flow of electrons. It's going to sort of slow down this flow of electrons. So resistance in some ways is almost like friction in that we have these things moving back and forth. So when we think about how to calculate resistance, we have to think of sort of what things would affect their ability to flow through a wire. So resistance is going to be involving a couple different things. First, something we'll call the resistivity that we'll use rho for. So resistivity, and that's a property of the material itself. How well does the material itself carry electrons and electrical charge? L, which is the length of the thing it's flowing through, so the longer the wire, the longer the actual resistor, the bigger its resistance. So that's just length like we're used to. And then divided by the area, or better put, the cross-sectional area of the actual wire or resistor itself. And so those three things are going to factor into it, because it's how well does the material carry it, how far does it have to carry it, because the further it has to carry it, the more bumps and things are going to happen along the way, and the cross-sectional area of it, because the narrower this space to move through, the smaller this area, the harder it is for all those electrons to squeeze through, and so the more resistance you're going to encounter. The unit for resistance is an ohm, which we use the capital omega in Greek to indicate. So however many ohms a resistor is how we measure its resistance. This brings us right into Ohm's law, which is looking sort of at how voltage, current, and resistance all work together. So the first thing we can think about, and it just kind of makes sense, is that our current is going to be directly proportional to voltage. In other words, the voltage is going to drive the current, so the bigger the voltage, the bigger our current. Voltage, by the way, is in a way a measure of the potential energy, or a difference in potential energy from the start of the circuit to the end. So the bigger that difference in energy, the better it's able to push those electrons around, the more energy it has to push those electrons around. Current is also going to be proportional to 1 over resistance. We say 1 over resistance because they're going to be inversely proportional, right? The more resistance you have, the harder it is for current to flow. So if we put all of that together, we get I equals V over R, or usually we write it as V equals IR. And this is called Ohm's law. So voltage is equal to current times resistance. And this is really very useful when we're analyzing a circuit to calculate what we call a voltage drop when current goes through a certain resistor. So when it goes through a resistor, this voltage is going to drop a little bit from what it was, and this is a way you could calculate it, knowing how much current is flowing into it and how much resistance that resistor offers. One way resistors work is by dissipating energy out of the circuit by getting rid of some of that energy, usually in the form of heat. That's why, in things like computers and that, you have to have a fan on them, is because they're going to generate a lot of heat from all those resistors and all the electrical energy moving through there. To calculate electrical power, we think back to sort of our original definition for power, and that power was an energy, let's call it a potential energy in this case, per time. In this case, electrical potential energy is QV, charge times voltage per time. And then you'll notice Q over T is sort of what we had for current. So one form of calculating electrical power would just be current times voltage. So current times voltage would give you the electrical power generated in that particular circuit. We also, from last time, have Ohm's law that says V equals IR. So we could substitute that in and say that power equals my current times my voltage, which is IR. And the result then is power equals I squared R. And that would be, for example, a good way to calculate how much power is dissipated by a resistor, how much power a resistor takes out of the circuit. And it has to do with how much current is flowing through and the resistance of that particular resistor, right? A higher resistance, more power dissipated. The more current flowing through that resistor, the more power it can dissipate, because the more it's going to be able to hold up that flow of energy. One other way to write it, instead of writing V over R, I could say that I is equal to V over R from Ohm's law, and plug that back into my original form. So that's one form of power, second form. And then we could say that power equals my current, V over R, times V. And so that gives me V squared over R. And again, that could be power dissipated by a resistor. So kind of how much power is in a particular circuit, and these two could be useful for, depending on what you know, the amount of power dissipated by resistors. But all sort of the same basic form from here, combined with Ohm's law.